this is where there is a big change, as far as I'm concerned, in the power electronics. I don't think the rest of the power electronics field really recognize it, but hopefully now you guys would recognize it from now on, the other people. That was the first time that in July 2010, I had the, courage to go away from Ćuk converter with a 2 transistor, 1 transistor, and 1 diode, and added one more switch. It happened to be diode. And as I showed you, and have added the, basically used the modified, as I showed you yesterday, modified original Ćuk DC to DC converter with a transistor and a diode, add one more switch, which replaced output inductor, and made it a 3-switch converter, 1 active and 2 passive, introduce isolation transformer, and that converter with the 3 switches, primary switch and 2 secondary switches, generated all what was required for converting alternating current on input to DC current on output, and having all functions needed. Eliminate a full bridge, make a power factor corrections, and at the same time provide isolation, just with the 3 switches. And what was needed at the time, what was used at the time, and unfortunately, the industry is peddling still the same, I showed you yesterday, full bridge rectification, then, a boost converter, power factor correction, and 8 switches, bridge conversion to provide isolation, 16 switches. And what I was finding disgusting, that even some companies claim that they have a bridgeless PFC IC chip. And of course, it wasn't bridgeless because it didn't have a bridgeless converter. But anyway, so here is a couple of things. This is my friend that I knew for many years, and he was an editor in many of these PCIM magazine and so on. So actually, he put a nice editor viewpoint at the time, recognizing that there was a important switch. And then I published this 4-part articles in it, and I got a cover page on that magazine, which was true bridgeless PFC. Why did I have to say true? Because a lot of other, before that, we're talking a bridgeless PFC converter, but it was bridgeless PFC IC chip controller, but the converter did have a full bridge on the input, because the whole point, as I discussed yesterday, that I invented a converter that has a bridge eliminated, although it was like a ghost present, because there's still 2 diodes on the output, which are changing association such that it looks like, it smells like it has a full bridge switch, full bridge diode, and all the losses, but didn't have any of that, and operates like as though it has a front-end bridge rectifier. And what was really key is to provide alternating current, which is directly in phase with alternating voltage. And here in the green side is alternating voltage, and unity power, having a power factor protection, power factor control, making that the current drawn from a sinusoidal line voltage is proportional to the voltage at any. So therefore, that is by definition. And here is a prototype, of that. And the first prototype we made was a non-isolated version. And of course, as I described yesterday, here is a. You saw it already, except this is now a nice article, right? Okay, let me do this. Hopefully, I can use up and down, and let's see if that works. Yeah, that works. I can go up and down with my keyboard, and then it will show on the big screen. So basically, I showed that yesterday, and remember the key point was we replaced this output inductor with make it simpler, but by replacing output inductor, that single step in original converter of the Ćuk converter that single step enabled now just step up. And remember, I discussed why the step up conversion is needed, because then varying AC voltage from 0 to peak and back to 0, it boost converter is such that it always step up voltage. So then power factor correction is basically saying changing duty ratio in such a way that you always step up, whether it's low voltage on input or peak voltage on input, you always get fixed voltage on your output. That's the definition of a power factor correction. And that's why you need the step up function. So this does that. And as we discussed, without this little resonant inductor, it'll be inefficient and won't be useful. But just little resonant inductor, which explained yesterday, it actually makes things work. And here is the converter. But now, what kind of controller we need? We need a true bridgeless PFC integrated circuit controller, which now works for this because it's not having a bridge rectified like a regular controller, you know, because I'll operate on half a cycle. This has to operate on both cycles. We did that and have a modification of IC circuit or controller to do that. So we made a bridgeless PFC controller and then basically make the unity power factor. As you can see, current is controlled with the voltage, and that is by definition the most efficient way that you should operate. And and here is a little review of why do we need to eliminate the bridge, simple bridge rectification. Simple bridge rectification actually says this: you are only conducting the current at the top of the sine wave voltage. In fact, at the peak of sine wave voltage, you start conducting this and rectifying it, and then after a little bit of a sine wave voltage drops, the current stops, and then you're waiting for next cycle that you're going to draw the current. Bad news. You're drawing the current in the pulses, which are at same frequency as sine wave voltage on the input, but the pulses of current at same frequency, but they are the high peak currents. And therefore, these high peak currents have a tremendous, by Fourier series, you have a tremendous number of harmonics. So you have, of course, because it's even odd function, that odd function has only odd harmonics. So you have first harmonic and third harmonics and fifths and so on. But all harmonics are very high in magnitude. So you have, what happens that if you do rectification, remember how I told you it's bad when we use the, in my laboratory, Caltech, we use the bridge rectification, or instead of that, we use switching converter, which was drawing the, how you say, noise, pulses from a utility line and contaminating utility line with the high frequency pulses. Here, utility line is compromised or really made to carry a lot of harmonics on utility line, which will cause distortion and noise, unwitting noise. So what is really needed is really to have, as we show here, that sine wave current drawn with sine wave voltage and coincide at the instant switching. So this is eventually what was realized. Power factor correction, when switch is on, you have this circuit, and when switch is off, you have this circuit. And I will show you next time the more details, but just to give you first order of understanding, what is happening is, remember, this is voltage waveform on PWM inductor. It's switching between high DC voltage and switching between high DC output, So these both voltages are very high in magnitude. Yes, there is a volt-second balance during on time and off time. And you see this area is a flux from positive flux and negative flux, as you know, has to be balanced. But what is happening with this bottom waveform, which I'll just show you? This bottom waveform is